In this measurement, I'm using our RTZP2 demo board, which allows me to measure data signal and power rail from USB 3.2 Generation 1 memory stick. In this setup, USB memory stick is connected to Type A connector at left-hand side of the test fixture. Board is powered by connecting USB cable to Type B connector at right-hand side. Oscilloscope analog channels 3 and 4 are connected to TX line, consisting of single-ended coaxial access points to 50 ohm transmission lines, including SMA connectors for oscilloscope connection. As soon as memory stick is powered, it sees 50 ohm single-ended or 100 ohm differential termination, and then it starts automatically link training bit sequence. By using this demo board, I'm able to measure USB data signal without setting USB memory stick to special test mode with some external stimulus. I have also modified this demo board in order to measure USB power rail. Therefore, this blue coaxial cable is soldered directly to +5 volt line. With this arrangement, I'm able to connect RTZPR40 power rail probe directly to SMA connector of blue coaxial cable. Power rail probe is connected to oscilloscope analog channel 1. Let's next set our RTP scope for power rail measurement. Alright, jumping to a scope screen. Since power rail probe is connected to oscilloscope analog channel 1 and TX data line from USB stick is connected to analog channel 3, we have to activate those channels. Next, I'm going to adjust the vertical scale for analog channel 3. Let's put 60 millivolts per division for this one. From this orange trace we can see that the USB stick is transmitting data and everything is functioning as it should be. Let's next concentrate for analog channel 1, meaning the power rail probe measurements. I'm going to take a look at the properties of our power rail probe. So for that one I will go to the vertical menu and for probes submenu. And from here we can see that the RTZPR40 power rail probe is connected to the oscilloscope analog channel 1. Bandwidth for this probe is 4 GHz. AC coupling is switched off. It means that we are also measuring the DC properties of the signal. Next I'm going to activate probe meter. And from here we can see that the voltage level in the USB power rail probe is 4.984 volts. The trace is still not centered into the screen, and for that one we have a handy function which is called copy to offset, so I will press that one. By pressing this knob I can center my trace into the scope screen without any further adjustments. Let's adjust a little bit this trigger level there. We can minimize the voltmeter measurements, then we can set our horizontal scale, so we can set for example 10 microseconds per division, and we can start seeing that there is some ripple in the USB power rail. Next we can adjust our sensitivity a little bit more now, so let's put 10 millivolts per division as a value for that one. Let's fine tune the trigger point here so we can get a stable trace in the screen. For power integrity measurements, the major concern is to find worst case violations. By increasing the waveform intensity, this can give you a better view of worst case violations that happen less frequently. So next I'm going to adjust the intensity of this channel 1 trace, and for that one I will go to the settings menu and for signal, and let's put 90% over there. Another way to get additional visual information about power rail is to turn on color grading. So let's do this one now. In this example, it's much more easier to see transients when color grading is turned on. This means in practice that pixels that are hit less frequently can be identified more easily. And in practice this means also that you can see how often different anomalies are occurring in your signal. Next I will measure peak-to-peak voltage for this ripple signal. And for that one, I will go to Measure menu, Advanced Setup, and inside the measurement group 1, we are using channel 1 as our source signal. And next I'm going to add peak-to-peak measurement. Let's disable the amplitude and then turn on the statistics for this measurement. Let's reset the statistics a little bit and wait for wave count to increase. And from this measurement result, we can see that the maximum peak-to-peak voltage for this ripple signal is around 46 millivolts, as shown here in this column. Now it would be really cool to see what's happening in a frequency domain. So first I will disable our automated measurement, and then I shall activate FFT. Start frequency for this measurement is 0 Hz, and as a stop frequency I will use 5 GHz since our PowerRail probe bandwidth is limited to 4 GHz. And for the RBV I will set 120 kHz here, and now I will deactivate the FFT trace. Next we have to rescale the FFT trace a little bit in order to see better what's happening in there. So from this FFT trace we can see that there are a lot of different things happening here between 0 Hz up to 3 GHz. This means in practice that the data signal from a USB stick is coupled into the PowerRail. We can also see that there are some signal spikes appearing around 2.4 GHz and 900 MHz here. Next I can enhance my frequency domain measurement by activating spectrogram. So for that one I will go to the FFT menu, spectrogram, and turn it on. So here in the middle part of the screen you can see the spectrogram view, and for this one the x-axis is frequency and y-axis is time, and third dimension is color, and that means an amplitude of the signal. So next I can adjust my spectrogram trace intensity a little bit so we can see more better what's going on over there. So let's put 40% in this one. And from this view we can already see more clear what's going on in different frequency regions. So we have some signals happening in around 950 MHz, 1.8 GHz, 2.2 GHz, and also in the region of 2.4 GHz. This means in practice that signals from mobile network cellular stations and wireless local area network is coupling in to my PowerRail. So this and many more measurements you can do with our PowerRail probe. Okay, let's go back to presentation.